Hi everyone, we are still in the introductory topics to Calculus 1. In this particular section, we are going to look at equations that involve logarithms and exponentials, and we are going to examine more complex situations than were presented in previous videos. First, let's take a look at the properties that can be applied to logarithms. We're going to start off with the logarithm applied to a product of two terms. So here, logarithm in base a of the product of x and y can be replaced by the sum of two individual logarithms, still in base a, applied to x and y individually. In the same manner, we can replace the logarithm of a quotient into the difference of these two logarithms. Again, the base is maintained, so base a initially is now base a on both terms on the right, and the dividing term is the one that is subtracted in the logarithm on the right-hand side. If a logarithm in base a is applied to a term that has an exponent, well, the exponent can be moved to the front and act as a coefficient. And finally, this is called the base change formula. So here we have log in base a of x, which can be replaced by the log of x and the log of a individually in a quotient with a new common base b. b is completely arbitrary, so it could be a base 10 or base e. Now these properties are particularly helpful to simplify expressions and to solve equations that involve several logarithms. Also useful to perform computations. As you've probably noticed, your calculators only have logarithms in base 10 or in base e, and therefore that fourth property may be convenient if you need to do a calculation on a log whose base is actually different than e or 10 themselves. Let's start off maybe by using the properties in order to simplify expressions. So here we have at the numerator 3 log of 6 minus log of 36. It's understood that both these logarithms are in base 10, and all this divided by log in base 5 of 6. So first and foremost, we probably would like to combine the terms on the numerator, but they are not exactly equal. Log of 6, log of 36 are quite different, and there is that 3 acting as a coefficient of the first logarithm. So here I've used the property that allows to displace a coefficient and make it an exponent, or vice versa, to write 3 log of 6 as log of 6 to the power 3. 6 to the power 3 is 216. Okay, so now at the numerator we have the difference of two logarithms. Now if you recall, one of our properties says that a difference of two logarithms is equivalent to the quotient of those two arguments placed in one single logarithm. So log of 216 over 36. For now I've left log in base 5 of 6 at the denominator untouched. 216 over 36 is 6, so log of 6 divided by log of 6 in base 5. Perhaps we could leave the answer as it is, but we could also notice that there are further simplifications we can do. Now, the numerator and the denominator do not have the same base. They're both logarithms, but at the numerator in base 10, at the denominator in base 5. So I'm going to use the base change formula to rewrite the denominator, and I'm going to choose base 10 as the b. Okay, so notice how log of x in base a has become log of x over log of a and in base 10. And now we have a term divided by a fraction, so we can multiply by its reciprocal and finally eliminate the common log 6's to get a simplified result. Okay, something more algebraic this time, where we have an equation to solve. So we're going to try to solve log in base 10 of x minus log also in base 10 of 2x plus 1 equal minus 1. Very hard to solve an equation when we have x's separated or found in different terms. So possibly a good first strategy would be to use the fact that the difference of logs can be combined as the log of a quotient. So that's a property that we enumerated earlier. If we're going to solve for x, we will have to get rid of the logarithm currently acting on the x's. Now, because log is in base 10 in this case, we will use an exponent in base 10 and apply the left and right hand terms to them. Okay, so log of x over 2x plus 1 is meant to be equal to minus 1, so making these the exponent of the same base 10 maintains the equality. Recall how base 10 exponentials and base 10 logarithms are inverse functions and therefore reduces to x over 2x plus 1. As for 10 to the minus 1, that is another way of saying 1 over 10. Okay, so we've managed to do the hardest part of the job here, which is to get rid of the logarithms themselves. Now we have expressions that are more manageable. So we can cross multiply, regroup like terms, and eventually just solve for x. Always worth that extra minute to replace x by 1 over 8 in the original equation to verify that you do indeed get minus 1 as a result. Okay, here slightly different situation where rather than having an expression with logarithms, we have an expression with exponential functions. And above all, we also notice how the exponential functions have different bases. On the left, base 4 exponential. On the right, base e exponential. Okay, and our goal is to solve for x. Right, so I've decided to apply a logarithmic function in base e to both sides. The choice of base e is somewhat arbitrary. It could have been in base 4 as well. Could have been in base 10, in fact, if I had wanted to, but I chose base e, so an ln function, because at the very least it will be the inverse of the base e exponential, but we'll get to that later. On the left-hand side, we can take the exponent of the 4 and make it a coefficient for ln of 4. So that's the property that allows to displace exponents and make them coefficients. On the right-hand side, you'll notice we use a very, very different property. 3 was multiplying with e to the 2x minus 3. So we've used the property of products contained in a logarithm that can be replaced by a sum of two individual logarithms. Okay. In this next step, we have observed that ln, a base e logarithm, and e to the 2x minus 3, a base e exponential, are inverses and therefore cancel to produce 2x minus 3. Okay, so this is much more convenient now. The x's are not contained in exponents anymore, but we do have x's on both sides of the equality symbol, so we will regroup on one side all terms that involve x's and put all constants on the other side. And then we can factor the common x and isolate x by dividing the 2 minus ln of 4 expression. As we did before, if you want to verify that you didn't do any silly algebraic errors, perhaps take the answer and replace it in the original equation to verify that it does indeed reveal something true. In this last example, we're going to look at something a little more complex, actually quite more complex. So we're going to identify the domain for the function x over ln of x, 7 minus x minus ln of x minus 1. Now when you're looking for domains, you want to look at restrictions that have to be imposed. So restriction number 1, recall that logarithms are only defined when their arguments are positive. So we have to impose that 7 minus x stay positive. In other words, x must be less than 7. The second logarithm must also be well defined, so x minus 1 has to stay positive. Therefore, x is greater than 1. And finally, we don't want the divider in its entirety to be 0. We don't want a division by 0. So the difference between ln of 7 minus x and ln of x minus 1 must not be 0. Ln of 7 minus x, therefore, must not be equal to ln of x minus 1. And using base e as an exponent, as an exponential function to both sides, we will then realize that 7 minus x must not equal x minus 1. So the rest is just moving terms around, regrouping like terms, and finding the restriction that is imposed. So x cannot be 4, otherwise we would have a dividing 0. Alright, so here are the restrictions we have. X must be less than 7, greater than 1, and not equal to 4, which gives us the domain for our function. So 1 to 4 exclusively, or 4 to 7 exclusively. Alright, last situation. So here we're going to solve an inequality where log of x and log of 2x plus 1 must be greater than 1. Okay, and now before we solve the inequality itself, we have to remember where these terms are well defined. So first of all, log of x individually is only defined for x's greater than 0. And log of 2x plus 1 individually requires that x be greater than minus 1/2. That's to make sure that the content of log 2x plus 1 is positive. So if we compare these two restrictions, we realize that x actually has to be greater than 0 in order to satisfy both. So that's the domain of the expression on the left. Now, as for solving the inequality itself, perhaps we can start by using the property that allows to replace a sum of logarithms by a product. Okay, so we have let me just go back here. So we were adding two logarithms, and those can be united as one logarithm where the arguments are multiplied. If we're going to find restrictions on x's, we're going to have to, for sure, find a way to get rid of the logarithm. So this logarithm is in base 10, and therefore it would make sense to apply a base 10 exponential to both sides. And that's what we'll do. So base 10 exponential with the expressions found in the earlier stage. On the left, the combination of base 10 log and base 10 exponential cancel. And on the right, 10 to the 1. Okay, and now we can expand the terms and regroup them on one side. And using the sum product method, we can find a way to factor the left-hand expression. Okay, so here I've emphasized quite a bit in previous videos how important factoring is, and we actually are faced with some factoring again. Grouping reveals that x minus 2 is common, which can then be simple factored, and we find that 2x plus 5 times x minus 2 must be greater than 0 as a restriction. Okay, so two zeros are observable in the left-hand term, so minus 5 over 2 and 2. And when we test for signs, we find that positive outcomes occur left of minus 5 over 2 and right of 2. So here's what we've got. We've got restrictions to solve our inequality that are x is minus 5 over 2 and well, actually left of minus 5 over 2. Or to the right of 2. But we also had domain restrictions that forced x to be greater than 0. So overall, the overlap of these two restrictions